Welcome back, everyone. We're going to wrap up our discussion of periodic motion and also our semester in mechanics by talking about damped and forced oscillation and resonance. So we want to look at how it is that oscillations die out, and we also want to look at the concept of a driving force and how that can cause resonance. So first of all, we want to introduce the idea of damped oscillation. So in real life, systems are going to have dissipative forces, such as friction, that decrease the amplitude of vibration. So this decrease in amplitude is called damping, and the motion is called damped oscillation. And we characterize this by a damping coefficient, B, which is related to the amount of friction. So you can see in this diagram that we have illustrated an oscillator with a little bit of damping. Okay? So it turns out that K and M, the spring constant and the mass of the object, they have a lot to do with this constant B. And we'll get into the details of that. Actually, I'm sorry, we won't get into the details of that. It's a bit beyond the scope of this course. Okay? And one thing that we can notice right away is that with larger values of damping, the amplitude is going to decrease more rapidly, and that's called our envelope. So this is light damping here, and more damping, it's going to decrease more rapidly, and you can see that it's an exponential function. So a larger number means it's going to decrease faster. You can also see that the period is increasing, and it's kind of hard to see here at this first peak, but if I erase my prior drawing, by the time we get to this third peak, you can see that it has shifted, the purple is shifted to the right. Okay? And what happens is that the energy of these damped oscillators are going to decrease. Okay, so we're just going to introduce the equation of motion for damped oscillation, but we're not going to get into the derivations of this very much. You need to really study differential equations a little bit more before getting into that. But I will point out that this math is exactly the same as for RLC circuits, which we'll see at the end of second semester as well. So this is pretty crazy. You've got the acceleration from m d squared x dt squared, that's basically your ma. Okay, you've got your damping right here, so minus basically bv. You've got your spring force, kx, and then you have fd, which is like a driving force. So you have four terms. Okay, you've got a second derivative right here, you have a first derivative right here, you have a variable, and then you even have time. So putting all that together tends to be pretty complicated. So C is the damping term. Usually we write it as negative BV, but you can also write negative CV. Okay, this driving force represents what happens if you apply force to the system at a constant driving frequency, omega. Okay, now this omega is different from what we call omega naught down here. And as a matter of fact, if F is 0 and if C is 0, then you start with what we began the chapter with. Okay, you get basically MA equals negative KX. And in that case, you get omega naught equal to root K over M. However, if you have a driving force that matches the natural frequency, you get resonance. And so resonance occurs if the frequency of the driving force, so omega, if that gets close to the natural frequency of the system. And remember that this driving force Fd had the form F cosine omega t, not omega naught, but just omega. Whereas when we're talking about x of t at the start, we were talking about a cosine of omega naught times t, although we weren't calling it that. And so what you can see is that as the damping coefficient goes up, resonance has less and less of an effect. Okay? So we have here amplitude versus the ratio of driving frequency to natural frequency. Okay? And if B is equal to 0 and omega d is equal to omega naught, then the amplitude is going to tend to infinity. So that's like those commercials in the day where you could break glass by singing. I think it was a Memorex commercial. Who knows if Memorex is still around, but that's what that was all about. Okay, so a couple of real-life examples of damped oscillation or resonance. Well, we have swings. Okay, and so if you are pumping your feet on a swing at the exact right frequency, then you can achieve resonance. Okay, every time you pump your legs, you add to the amplitude of the system, but only if you do that at the right frequency. Okay, if you pump your legs when you're at sort of the end of your swing, it's not going to help too much. You got to do it kind of as you're going through the midpoint. Then we can have shock absorbers on cars, and there's different types of damping. There's critically damped and overdamped and underdamped, because when you're riding in your car and you go over a bump, you don't want the car to shake up and down forever, so you don't want amplitude versus time to be like do 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 do. What you want is a nice slow decrease that's just going to happen once. Okay? And then finally, as I mentioned, RLC circuits are a very good example of damped oscillation and resonance. RC circuits to a lesser extent, but RC circuits are really going to have kind of a decreasing value that follows an envelope, whether it's current or charge or voltage. These are all things that can vary as a function of time. Okay, well, we did it. We made it to the end of mechanics. So I hope that these lectures have been useful to you. And if you continue with the E&M portion of the course, we will start right up again in chapter 21 of our book by considering forces on charges and electric fields. So thanks for watching, and we'll see you next time.